please. Okay. So just for the record, welcome everyone to the African Plants Georeferencing Train the Trainers workshop. This is our first session, and we're going to talk about geographic concepts. These are some basic geographic concepts that we need to keep in mind during this whole course so that we can perform the georeferencing process, knowing all the factors that will be important. So to start, we're going to talk a little bit about representations of the Earth. And we can represent the Earth in many different ways. And there are a couple of concepts that we need to know about. One of those concepts is what an ellipsoid is. An ellipsoid is a three-dimensional geometric shape that has three independent axes and sorry, whose planar sections all form either an ellipse or a circle. We're going to see this graphically in a moment. So the Earth can be represented as an oblate, that is flattened at the poles, ellipsoid of revolution. This means that it's produced by rotating an ellipse around its semi-minor axis. So we have an ellipse, and if we rotate it, we have an ellipsoid of revolution. So we can represent the Earth with this ellipsoid of revolution. So here, for instance, we can see different kinds of representation. This is a sphere where we have three axes, and all the axes have all the dimensions have the same size, right? If we take the poles and flatten it on the poles, we will have two dimensions that are equal and the other one that is different. This is a spheroid. For an ellipsoid, in the three dimensions, we can have different values. So this is a representation as an ellipsoid, and is what we usually use this ellipsoid to represent the Earth. Another key concept that we use in representing the Earth is a geoid. A geoid is a global equipotential surface that approximates mean sea level. That means it's a surface that is at the same mean sea level, that unites all that mean sea level. So this surface everywhere is perpendicular to the force of gravity. We can see how it looks on Earth here, and we will see it graphically a little later. So this geoid provides a surface that is actually smoother than the Earth itself, the actual surface. For example, the Earth has its highest peak at the Everest and its lowest depth at the Marianas Trench, but that is not what we see on the geoid. The geoid is smooth, and so it has an upper limit of much less height, and same for the lower point. So we see that it's smoother than the actual surface of the Earth. Now, there is an important concept that is called undulation. That is the height of a geoid relative to its reference ellipsoid. Don't freak out, we're going to see what this means. But it's basically comparing how the geoid is with respect to that geometric ellipsoid that we can use to represent the Earth. So suppose that this is the surface of the Earth. We have a mountain here and the ocean here and there. And so if we use the geoid that is based on the mean sea level, this is going to be represented like this, at mean sea level, and is in every point is perpendicular to the gravity. Now, if we represent the ellipsoid does not follow the mean sea level, it's just a geometric shape. So in green, we have here the ellipsoid, and we see that there are differences between the geoid and the ellipsoid. And this difference the difference in the angle when we plot the perpendiculars is called vertical deflection, and the undulation is that difference between the ellipsoid and the geoid. And why is this important? Well, we can represent the Earth using the geoid or the ellipsoid. And particularly for elevations, this is going to be essential to know which of the two we're using. For example, if we're standing here on top of this mountain, the elevation will be different if we measure it from the geoid or from the ellipsoid. And in different points on Earth, that difference is different. Here is much less and here is much more. So it will be very important to understand, particularly for elevations, if we're representing Earth using one or the other. Now let's go to some important topics that are coordinate systems, coordinate reference systems, and associated concepts. So let's first define what a coordinate system is. A coordinate system is a geometric system that defines the nature and the relationship of coordinates that we use to define positions uniquely. So there are many coordinate systems, and some of them we're very familiar with. For example, the number line is a coordinate system in a single dimension. We have others that are the Cartesian ones that are in 2 dimensions, X and Y, and we can define where a point is by providing the values for each of the axes, each of the dimensions. But there are many others. There are polar ones that have one dimension and an angle. There are Cartesian orthogonals, and there are many other coordinate systems or geometric systems. Now, a coordinate reference system is a coordinate system that is defined in relation to a datum. We're going to see the concept of datum a little later, but keep this in mind for a couple of slides forward. So we're saying coordinate system, coordinates reference system, and we can specify a geographic coordinate reference system, which is a coordinate reference system, okay, that uses geographic coordinates and is based on a geodetic datum. We're going to see datum a little later, but this is an important thing. It's geographic coordinates for a geographic coordinate reference system. And so what are coordinates and what are geographic coordinates? Well, coordinates are sets of values that define a position within a coordinate system. When we were seeing the axis X and Y, we have a value for X and a value of Y, and those are coordinates in that system. For geographic coordinates, we talk about latitude and longitude. Those are the geographic coordinates. So we're going to see a little bit more how this latitude and longitude are defined. So suppose this is a representation of Earth that is a spheroid. We know that it's not a sphere, but just for the sake of explanation. The middles of the Earth horizontally are the equator, and we can set meridians. Here is plotted the Greenwich meridian, which we usually use as the 0 meridian. And we have a point here in yellow that is the point that we want to describe. It's a location on the Earth, and we want to provide the latitude and longitude. That is the geographic coordinates. So we define the latitude as the angular distance of a point north or south of the equator. In this case, is north of the equator. It's an angular distance. Similarly, we define the longitude as the angular distance east or west of the prime meridian, which is here represented as the Greenwich meridian. So both latitude and longitude are angular distances from a given reference, the equator or the meridian. Now, these coordinates, as you probably already know, can be expressed in different formats. One common format is degrees minutes, and seconds. Another one is degrees and decimal minutes, and also decimal degrees. Here we have some examples: degrees, minutes, and seconds. Degrees, decimal minutes, they are usually accompanied by a letter that signifies the hemisphere. In this case, we're talking about latitude, so it can be south or north. If we were talking about longitude, it would be east or west. When we use decimal degrees, we usually summarize that hemisphere using a minus sign if the latitude is south or if the longitude is west, and we don't use the letter. So that about the format. And there is an important attribute also of geographic coordinates, that is that they have limit values. We talk about latitude is with respect to equator, north or south, and so we can only go as far as the pole, the North Pole or the South Pole. So we cannot go beyond 90 degrees or minus 90 degrees. So those are the limits for latitude. For longitude, we can only go half the spheroid around, so that is 180 degrees or minus 180 degrees. So any latitude or longitude that is outside these ranges cannot be correct if we're talking about geographic coordinates. Now, coordinates can be given with different precisions. And what is the precision? The precision is the fraction of a degree that corresponds to the number of significant digits in the coordinate source. So for example, here we have a decimal coordinate, and we have 1, 2, 3, 4, 5, 6 decimal places. And we're saying this coordinate here has an 8, number 8, but it could have been number 7, or it could have been number 9, etc. So this is the most precise digit that we have, and we can miss it by one more or one less. So our precision is 6 places for this coordinate in particular, and here we're determining where the precision is. If we have a coordinate that is in a different format, degrees, minutes, and seconds, here is the most precise digit that we have. But precision is defined as the fraction of a degree. And here we have it as a fraction of a second. So we have to convert seconds to degrees to be able to provide the precision. So we know that 3,600 seconds are 1 degree. And so 0.1 seconds, which is the precision in this coordinate, how many degrees is that? So this is how we calculate as fraction of a degree the precision for a coordinate that is in another format. We're going to come back to this, and you can ask if you haven't understood this concept. Now, going back to the coordinate reference system, geographic coordinate reference system, we were saying it is a coordinate reference system that uses geographic coordinates, latitude and longitude, and it's based on a geodetic datum. And what is a geodetic datum? Well, let's start with what is a datum alone. A datum is just a set of reference parameters that we use to calculate other parameters. This is pretty broad, but this is how it is. And so the datum for our coordinate system will define the position of the origin, the scale, and the orientations of the axis of that coordinate system. We're going to see it graphically. Hold on a second. Now, in particular, a geodetic datum uses a reference ellipsoid. There are other kinds of datums. There are vertical datums that use other surfaces as a reference. For example, they can use mean sea level or use a geoid. They can use ellipsoids or any local reference surface. Let's look at it graphically now. We have a representation of the Earth, and we can see here one datum that uses a reference ellipsoid. And so we're saying it defines the position of the origin, the scale, and the orientation of the axis of that reference system. If we were using some other datum, for example, this datum B is using another reference ellipsoid, and so it is defining the position of the origin, the scale, and orientation of the axis differently because it's using another reference. So each datum will have its reference, and hence it will define these three things differently. Now, why is this important? If we overlap these datums, we see that they differ quite a bit in my graph anyway. So we can see that we can have differences in origin, in scale, and in orientation of the axis. Now let's bring it to a particular case. We're here, standing just here on Earth, on that little yellow dot. Now, if we want to represent that dot with the different datums, and we want to provide coordinates for that dot, if we use this first datum up here, the green one, we will have a latitude, a longitude. We were saying they are angular distances. If we use datum B, we will have a latitude and a longitude. Now, they use different references. So when we plot them here, we can see that latitudes are different depending on which datum we are using. And similarly, longitudes are also different depending on which datum we're using. Therefore, even though we're standing on the same spot, on the same location, the coordinates will be different depending on the datum that we use. So it's very important to keep the datum in mind and always report it. Now, which datum are we using? Well, there are more than 750 distinct geodetic datums. One of the most used ones is the World Geodetic System, which we usually know as WGS 84, but there are many, many others that we could be using. The WGS 84, the reference system is described by this code here, EPSG 4326, is a horizontal geodetic coordinate reference system that we use globally. And GPS measurements are usually based on this reference system. We have to be careful because WGS 84 can be referring to the coordinate reference system, but also to the geodetic datum that that reference system uses, or the ellipsoid that that datum is based upon. So when we see WGS 84, it could be any of the three things. So careful with that. Now, these are some characteristics of the WGS 84. I'm not going to go into them in detail, but it has a particular coordinate origin that is the center of mass of the Earth. It takes a prime meridian that is not Greenwich, is a little off Greenwich. We have which is the datum surface, which is the geoid that it uses, etc. As I was mentioning before, there are some codes that define special reference systems. They are called EPSG. And these EPSG have uniquely identified the coordinate reference systems, including their datums. And we can always transform between coordinate reference systems. And so in the web page of EPSG, that is epsg.io, we can see all datums that are available, each one with their characteristics, in this case WGS 84, and we can also use this page to convert between coordinate reference systems. So if we have coordinates in a particular system, we can get them in any other. So this might be of use to when we are georeferencing. Okay, this has been a rough beginning. I know that I have mentioned a lot of concepts that are probably new. Take it easy and come back to the video later if you have questions. We're going now to move to some concepts that are more that are closer to all of us. But keep being there with me. Stay with me. So we're going to go to maps. Maps, we probably have all seen maps at some point, either paper maps or digital maps. But there are some important topics that we need to mention about maps. So let's start with a map is a representation of the Earth on a planar surface that shows us the spatial relationships between different elements on that map. And there are three features that we need to pay attention to. One is the projection of the map, another one is the scale, and finally the orientation. So let's start with projections. Projections are transformations that allow us to bring something that has a particular shape, a spheroid, in the case of the Earth, onto a plane surface. So it converts the location of points in a coordinate system that is on a curved surface to points on a plane surface. So as you can see here, we're trying to project this surface that is curved onto a sheet. So projections there are very many different projections. Here we're showing a classification that is non-exhaustive. And one of the characteristics that we use to classify projections is the preservation of metric properties. Based on this preservation of metric properties, we can have conformal projections. That what they do is they preserve the local shape of things, of elements on the map. We can have equal area projections that preserve the area in square meters, square kilometers. We can have equidistant ones that preserve distance, some that preserve direction that are called azimuthal, that preserve the shortest route, or compromise projections, which do not exactly preserve any of these completely, but they try to make a compromise, a balance between keeping the shape and keeping the area and keeping the distances, etc. So this is a little more detail. For example, the conforming preserves shape, but by preserving shapes, it distorts the sizes of the elements. For the projections that preserve area, they distort the shape. We have the same square kilometers, but the shape is a little distorted. For equidistant projections, we preserve distances, but we also distort shapes. And as we were saying before, for compromise projections, we try to balance all those different distortions, but we still have distortion. And usually we have more distortion at the poles than at the equator. We're going to see some examples in a moment. So aside from this classification by which metric properties are preserved, we can also classify projections by the surface on which we project. We can project directly on a plane, which are planar. We can project on a cone, so they are conical, and then we open up that cone to put it on a sheet. Cylindrical projections, pseudoconical, polyconical, there are many depending on the surface on which we project. Two of the most used projections are the Mercator and the Gauss-Kruger, which is a transverse Mercator. Mercator is a conformal, that means it keeps the shape. And so it has a series of characteristics, which are that the scale, north, south, and east, west are the same, that the stretching on the map is the same, north, south, and east, west, and that it has much more distortion at higher latitudes, that is at the poles. Well, these are just examples. We're not going to see each projection in detail, but just so that you have an idea. This map shows the Mercator projection in light blue against the real size of the countries in the world. We don't have Antarctica here, but you can see that the north part of the closest we get to the North Pole, the more distorted is the actual size of things. So that you keep in mind that what we're seeing in the map is not exactly the reality. And so, as I was saying, there are very many different projections based on what parameters they try to preserve and the kind of surfaces. Here we have a conical one that we see that then we flatten up. And so there are very many different kinds of projections. But something that is important is to keep in mind that distortion. So there is a method to measure or to represent rather the distortion, that is the Thesis indicatrix, which is a matrix that illustrates the distortions at different places of a map. So for example, in the Mercator, using the Mercator projection, we can see these orange dots here are much bigger. These represent the distortion, much bigger closer to the poles than at the equator. This is another projection, and you see that at different latitudes, we have different distortions in latitude and longitude than in other places. And this is going to be important to keep in mind. Just to show you some other examples, these are other projections and their corresponding Thesis indicatrixes of distortion. Well, so what's important to keep in mind about projections? All projections have some distortion. Some may keep some properties better preserved, but all of them always have distortions because we're putting something that is three-dimensional into a plane. Then, for small-scale maps, small scale, we're going to see scales in a moment, but small scales means that we're putting in a little piece of paper, we're putting a very big surface, like continents or the entire world. We usually use compromise projections that try to balance all those distortions. For national maps, it is common that we use transverse Mercator or some variant of it. That are conformal, that is, that they keep the shape, and they have little variation in scale when we're looking at small areas. When we look at thematic maps, we usually have projections that keep the area but have some shape distortion. I'm sure you have seen some national park map or those kind of resources that keep the area, the square kilometers, but well, it's not exactly a square, it's not exactly a triangle, the shape that we're seeing here, so they have shape distortions. As you can see, for different purposes, we can use different projections. So the projection that we're using is very tied to the concept of fitness for purpose. That is, we use the projection that is better for the purpose that we have for the objective that we want to achieve. So we have seen projection. We're going to talk a little bit about scale of maps. So scale is the ratio between the distance that we see on the map that we can measure with a ruler and the distance, the real distance on the surface of the Earth. So we represent it usually in this manner. So we have a number. 1 here represents 1 centimeter on the map, represents 100,000 centimeters in reality. That is a kilometer. So we use map, column, reality. That's the way in which we usually express the scale. And if we look on the maps, we will usually find a graphic scale, which is, well, we can measure that. On my screen, I'm not sure how much it measures, but on the map, it usually measures a centimeter. And we have here how many kilometers that centimeter is representing. So we have a graphic scale. And as we were mentioning before, depending on the projection of the map, we have more distortion on some areas with respect to others. So for example, if we're using the Mercator projection, when we get closer to the poles here, this is the equator, and here is the 80 degrees, a little bit more is the pole. As we get closer to the pole, we have more distortion. So that scale is not kept on all the map. That scale is for the equator, the one down here. And as we move north or south, the scale changes. So we can also find this kind of representation, which is more accurate than just having a single graphic scale for all the map, because this one takes into account the projection that we're using. So any map that we can consider a good map usually will give us a scale, in this case, a graphic scale, and ideally will also tell us which projection it is using. In this case, it tells us the projection with kind of ellipsoid and other features. So you should be able to find this on paper maps, at least. So now that we have seen the projection and the scale, let's talk a little bit about orientation, which might seem much easier. The orientation is the relationship between the directions on the map and the cardinal points in reality. So north, south, east, west. So for example, on this map on the screen, the north is up, is in the upper part of the map. So it's oriented with the north up. In these maps, in this one here on the left, if we are careful, we will see that here we have the indication of the cardinal points, and the north is to the right of the map. So what we're actually looking in the upper part is not the north, is the west. So we have to be very careful, especially with old maps, because old maps might not be oriented with the north up. And in this map on my right side, I believe it's a Chinese map, and probably these symbols here, unfortunately I don't read Chinese, but I suspect are the cardinal points, but I cannot be sure. So if I don't know, I cannot really know where northwest is, south is on this map. So we also have to be careful on how we interpret the positions and relative positions on paper maps. So, okay, you might be thinking, well, I actually never use paper maps anymore. Well, you might need them at some point, but let's go to Google Maps, which is something that we use probably daily. Google Maps in particular uses Web Mercator, and for Google Maps, north is always up. Meridians are equidistant vertical lines. And as it uses Web Mercator, areas near the poles are very exaggerated. So as we were seeing before, Mercator and Web Mercator and Transverse Mercator have a lot of distortion at the poles. And it's not conformal. It means it doesn't keep exactly the shapes of things, because it's using geographic coordinates with a data monospherical projection. So even though you see here APSG 3857, the coordinate reference system that is using is WGS 84, the one that we were mentioning before. So these are some characteristics of Google Maps just to keep in mind. Now, let's go to some concepts that we will need for describing locations. We have seen general geographic concepts, and now we're going to go to more particular things about places that we want to describe. So, what is a location? Let's start with that. It's something very basic. A location is a physical space that can be positioned and oriented relative to some point of reference. That location will have a description, a textual description, a boundary, a limit, an extent, there is an area, and a radial. We're going to see each of these concepts in the next slides. So let's start with the location description. Here in this map, we have a little town in Chile, in the Ñuble province. This town is called Buli in the Ñuble province. So we can represent this town with a verbal representation, which is the location description, which is this that is written here, Buli, Ñuble. That's a verbal representation of this town. Now, this is a town. So we can say that we have a particular feature, which is the object of observation, measurement, or reference that can be represented. So in this case, we have a town, but there are other types of features that are mountains, roads, craters, lakes, national parks. We can have many different types of features. And in this case, we have a town. The feature is a town, and this is the location description. We can also delimit this town, and that delimitation sets the boundary of the town. And the boundary is the spatial divider between what's in the town and what's outside the town, which is in the feature or outside the feature. That's the boundary. And the extent of this location is the space inside that boundary. So we have the boundary and the extent, that is an area. And also we will define a radial. And the radial is the distance from the center of a place to the furthest point on the boundary, on the limit. If we look at this, we can see that this center we can draw a circle around it, right? And so if we put the radius of that circle to the furthest point on the boundary, we can define a radius, right? And so that's why we call it a radial. Now, let's talk a little bit about centers. What are the centers of our locations? Well, we can define two kinds of centers. On one hand, we have the geographic center, that is the midpoint between latitude and longitude extremes. We're going to see this graphical in a moment. And we can define the corrected center. And the corrected center is a point within or on the border of the feature that minimizes the geographic radial. So let's look at our example of this little town. We have the boundary, and we can define, well, this is the minimum latitude that we have, and this is the maximum latitude. And equivalently, these are the minimum longitude and maximum longitude. Okay, so we can define the max and min geographic coordinates, latitude and longitude. And we can say, well, the center of this is this point right here. That's the geographic center. If we draw a circle that goes all the way to the furthest point on the boundary of the feature, we can define a geographic radial, right? From the center to that circle, to the that goes to the end. Now, is this the minimum circle that we can draw that encompasses this town? And the answer is no. We could draw a smaller circle that includes all the town still, but it's a little smaller. You can see that the yellow circle here is smaller than the red one, but it still contains all the town. Now, the center of this yellow circle is not the geographic center that we had before. It's another one. It's moved a little bit, and so it's corrected. And so we talk about corrected center for the circle, the minimum circle that encompasses the location, in this case, the town. And hence we define a corrected radial that is the radius of that circle that is centered on the corrected center. This is going to be important because we're trying to minimize, when we georeference, we're trying to minimize the uncertainty that we have, the error that is associated with our georeference. So now that we have seen some characteristics of locations, that are the description, the centers, the extent, etc., we're going to go through some other components that make up locations, that we will have to keep in mind as well during the georeferencing process. And those are the vertical components. And among vertical components, we're talking about elevation, depth, and distance above the surface. So when we talk about elevation, elevation is a vertical distance of land or water surface above a vertical datum. So for example, we can take here above mean sea level, and we can have an elevation of this peak of the mountain. So elevation can be positive or negative if we're going below that vertical datum. So if we go above it, it's positive. If we go below it, it's negative. And it can also be zero. If we are usually at sea level, we talk about zero elevation. On the other hand, when we're talking about depth, depth is a measure of the vertical distance below a vertical datum, and we usually refer to depth when we're talking about water bodies. And so from the surface between the water and the air, we measure depth. And depth is always not negative. That is either zero or positive. So if we are 10 meters underwater, our depth is 10. It's not minus 10, it's 10. We're always putting it in not negative values. And finally, the distance above the surface is a measure of a vertical distance over a point of reference. For example, our point of reference can be, for this little bird on the left, the surface of this of the land. For this bird on the water, it can be the surface of the water. Or for this surface down here, it can be the surface between water and land at the bottom of this water body. So distance above the surface can be positive if it's up from our point of reference, or negative. And the references will vary depending on the context. So we can have, as we said, land, or we can have water, and we can have aerial, air water, or submerged references, water substrate interfaces. Now let's look at some examples. We have here, if we're standing on this red dot on this mountain, our elevation will be probably positive if we assume that this is at sea level. So we will describe this as a positive elevation. We are at that elevation. Now, if we're observing a bird on top of the tree, the elevation will be the elevation of our reference land. So the elevation is at this point here, and the bird will be also at a distance above the surface. So the elevation is at the surface level, and we are, I don't know, 3 meters above at the top of the tree with a positive distance above the surface. Another example is if we are at this same elevation that we were before, we were standing there and we dig a hole to get some sample underground. And so we dig the hole and we are standing at this elevation, but we have a distance below the surface, in this case, where we take the sample. So the concept distance above the surface will be negative because we're digging the hole. The elevation will be the same, however. Now, if we're observing a bird flying on top of a lake, the elevation will be the elevation of the lake, because this is our reference surface. And the height at which the bird is flying will be a distance above that surface, which is a positive value in this case. And we're going to see a couple of examples more. If we are catching some fish in the middle of a lake, again, the elevation will be the elevation of the surface of the lake, which is our reference, and the depth will be the distance below that surface, which is always positive. Remember that depth is always positive. And then with the most complex example probably is we're at some point in the lake, we go to the bottom of the lake, and down there we dig a hole and we take a sample. And so the elevation is going to be defined by this reference surface, which is the surface of the lake. From there, we get elevation, and we can get depth, which will be all this depth up to the bottom, always positive. And from there, we will have a distance, in this case, below the surface. But now the surface changes because our reference surface is the interface between the water and the land. So this can be, for example, 20 centimeters, or in this case, minus 20 centimeters. So be careful because the reference surfaces that we use in this case are different. Okay, so with all that we have said so far, I suspect that you can infer that having coordinates is not the same as having a georeference. As we were seeing before, what coordinates represent is different, for example, if we use different datums. So if we just have coordinates, we cannot really know where we are. And also that having geographic data is not the same as having georeferencing data. And so we have to be very careful during the whole course. We will see some other concepts that will help us understand how to get to a georeference from coordinates and geographic data that we have, and how to generate georeference data that can actually allow us to place a record, an observation, or a specimen on a spot on Earth, or rather on a location, because we will see that spots are never dots. So given that we're talking about georeferencing already, let's define what georeferencing is. So this X here is a location that we want to georeference, and georeferencing means to associate a locality, this locality, for example, with a point in a physical space. So to be a little more specific, is to assign a numeric description of a place in a coordinate system. To do that, we have to consider, someone is unmuted, and if you could please mute your microphones, thank you. In able to assign that numeric description of this place, we need to consider how well does that numeric description actually represents the locality. And so we will have to measure an associated uncertainty. We're going to see this during the whole course. So let's make a full definition of georeferencing. Georeferencing a location means to assign a numerical description to a location in a coordinate system, describing its extent and minimizing the uncertainties that are associated. So you can see that in this definition, we have a couple of things that we've seen today, and I invite you to review when you have a moment, so that you can fully understand the depth of this definition. So just as an introduction, and we're almost there with this presentation, we're going to describe uncertainty sources later on the course, but so that you have an idea, uncertainty can come from coordinate uncertainty, from unknown datums, as we see. If we don't know the datum, we could be way off. imprecision in distance measurements. For example, if we have a description that says 8 kilometers south from this town, well, is 8 kilometers or is 8.1 or is, well, there can be imprecision in distance measurements. There can be uncertainty in the location extent, how big that location actually is. If we're taking coordinates with GPS, the GPS accuracy contributes to the uncertainty, and also imprecision in heading measurements. Heading is when we specify north, south, west, for example, 10 kilometers north of X lake. And so is it really north, or is it a little bit northeast or a little bit northwest? So there can be imprecision in heading as well. So all these factors contribute to the uncertainty, our uncertainty sources that we're going to see in quite a bit of detail later on. So with this, we finish with the geographic concepts presentation. We're now going to make a very short break. We're going to take 10 minutes. So we're coming back at my 10:10. So do your calculations. 10 minutes from now, and we will start with location description. So we're back here for the second half of the session. Here is John Wieczorek, who is going to give this part. So I will pass the microphone, and he's going to share his screen, and off we go. John, all yours.
Okay, testing first the sound. Are we okay? Okay, now I'll share my screen. I'm John Wieczorek. I had to come a little late because I had to deliver a small child to school, but I'm here now. And let's get right into our second topic of today, which should be not this. Give me 1 second. Something happened with my tabs. Okay, back to sharing screen. This time we should be better off with that. Okay now? Okay, so our second topic is about locality types and locality descriptions. And we're going to approach this topic from a couple of different perspectives. First, why are locality descriptions important? You've seen them already in the presentation that Paula made. For example, that textual description of Bulli in Nuble was a description of a place, a little town. So that's one example. So if we're going to have good locality descriptions, then we can have better georeferences. And that means that our precision is higher, our accuracy in describing the actual place that was meant is better. And that means that our net uncertainties about the description when we turn it into a spatial representation are diminished. So the two perspectives are, one, if you were to write a locality description that would be ideal for somebody else to georeference, what would it look like? And the other is, as the recipient of a legacy of locality descriptions, how do we interpret them? And what uncertainties come into play when we try to do that? But the point is to try to have the best possible description. So what are the elements of a good locality description? First of all, there's a verbal description, such as that named the features in the example Paula gave of Bulli, the town name. and then Ñuble, which was a higher administrative unit in the country of Chile. All those are parts of verbal description. Other things that might come into play are elevation, which Paula talked about a great deal, and we have a good grasp now of what we mean when we talk about elevation, of coordinates as well. We have the geographic coordinates that might be in different formats, but we also have other types of coordinates that are not necessarily latitude and longitude. And those will come into play at some point when we see our locality descriptions that we have to georeference. Paula talked about datums. There are two kinds. There's the geodetic datum that describes the model of the Earth that things are based on. And there's also the vertical datum that is a different model of the Earth that describes our reference for elevations. Another thing that can come into play if a GPS was used to capture coordinates is the precision with which those coordinates were captured and the accuracy of the GPS at the time that the coordinates were taken. And then finally, another thing that comes into play and is very important is the extent. If you remember Paula's presentation, extent was the area inside of a boundary that describes a place. Okay, so those are our basics. Now, the characteristics that we would like to achieve if we're going to create a very good locality description is that it's specific. It's a small place. It's as small as we can describe and not be including other things that aren't part of the place. It's precise in that we're not describing it in measurements that are less precise than what we need to actually get the specific place specified. Unequivocal means that there's no ambiguity. When I tell you the place, you should be able to reproduce it. You should be able to look at a map or whatever and find exactly the same place. That the description is complete, that I'm not leaving out any information that might introduce uncertainties, and that it's accurate. I'm actually telling you the truth. I'm not saying that the place was a market when it was further down the street. That I'm telling you the truth when I make my locality description. So here are some tips about how to use those characteristics to create a very good locality description, one that can be georeferenced with the least uncertainties. One is to use reference points that are very small. What does this do? It reduces the extent of the place that we begin with. Another good aspect of a reference point is that it's stable both in position and over time. If we use something that's going to change, something like a kilometer marker on a road, and roads change their locations, is not a particularly good choice. It's very small, but it's not necessarily going to remain in the same place over time. And then the final aspect is that it's easy to find on a map or gazetteer. Again, a kilometer marker is very specific, but it's very hard to find such things on maps or in gazetteers. So what we want are things that are small, stable in position over time, and easy to find on maps. The second tip is that we want to avoid unnecessary uncertainties by being imprecise. So if we're going to describe a place with respect to a distance from a very specific place, we want our distance not to be vague. We want it to use as much precision as we possibly can. And then finally, the other thing to do, or not do, is to avoid vague terms that introduce uncertainty on our part about where the place actually is, or that are not helping to describe the place. So if I say near or near the center of, what does that mean? It doesn't give me any scale, doesn't give me any real distance. It's just a descriptor that's not helping. further tips. If you just provide the name of a place, in some cases, that can be ambiguous because the name might refer both to a town and a river and a gas station and somebody's name and somebody's property. All of those things could have the same name, and they could be repeated several times in a country even. So wherever appropriate, we want to indicate if there might be confusion about what the name refers to, that in parentheses, we say what feature type it is. So I'll give an example from my experience because I can't come up with one quickly for Africa, but Long Island. Long Island is an island, and it's also a city. And so if I refer to Long Island in my description, I should say Long Island, and then in parentheses, the city, because I mean the city. So other things that might have confusion are rivers, especially in South America. There are many towns that are named as if it was the name of the river, national parks, and so on. Another tip is to avoid providing descriptions that have only a heading without saying how far. By heading, I mean a direction from a place, north of or east of, without saying how far. So the example here is west of Yaoundé. Okay, so now, in order for us to get a sound understanding and basis in things that we're going to end up interpreting and georeferencing, we'll talk about locality types. The quintessential guide for locality types and all of their variations and how to understand them and the recipes for georeferencing them are found in the Georeferencing Quick Reference Guide. And I think Paola can include a link to that specific document in the chat. That will be our Bible for georeferencing. So in that document, there are locality types and a quick review of some of the characteristics of features that we will need in order to do georeferencing and that we will get from deciding on what the locality type is. So features have boundaries, and the insides of the boundaries describe the extent or the area of that feature, and the boundary outside of it is not part of the extent. The features have centers, and Paola showed us two kinds of centers: the geographic center, which is generally not a very good representation because it doesn't allow us to create the minimum circle. And then there's the corrected center, which allows us to minimize the circle describing a feature. And both those types of centers have radials to a point on the boundary that is the furthest away from that center. In other words, it's the radius of a circle within which the feature is contained. And it's minimized when we have a corrected center. So this is a quick summary of all of the different locality types, and they're divided into 4 different categories. There are those that are based on geographic features only. There are those that have geographic features and offsets from them. There are those that are based just on coordinates, and then there's a set of ones that are complicated for one reason or another. So we're going to go through some of these things in a little bit of detail. So the first geographic feature only locality type is one that has a very obvious spatial extent. So that means that we can tell where the boundary is, and it's easy, and it's not ambiguous, and we can draw it with a polygon. So the perfect example of this was Paola's example of Buli, the little town of Buli. So in the quick reference guide, Georeferencing Quick Reference Guide, you're going to see diagrams such as the one on the right that show where the center is, what the radial is, what the minimum bounding circle would look like in these cases, where the boundary of the feature is, and a representation of the feature inside of it. So here's our most simple example in the diagram at the right. So examples of geographic features with obvious spatial extents are cities, towns, parks, ranches. Smaller things like tanks or wells or oases, and more utilitarian type things like airports, buoys, docks, and piers. And you can see examples of each of those things there. So all of those are features with obvious spatial extents. Then we get into the slightly harder situation of geographic features without such obvious spatial extents. So these are ones where it's a little bit more tricky to put the limits or the boundaries. And a perfect example of this might be a mountain. When we look at a mountain and we're nearby it, we have a fairly decent idea of where it is. We say, okay, that's the mountain. I can see it there. It's above all of the horizon, et cetera, et cetera. But when I look down on it from above, from a map, it's a lot harder to decide where that mountain ends and where the next thing begins. So that's the situation we have with geographic features without obvious spatial extents. So some examples of these are things that are just areas like a desert, where the boundaries might even be changing based on satellite imagery, and other types of regions. Ports, bays, and gulfs, it's sometimes hard to figure out where to draw the line. In the opposite direction from ports, bays, and gulfs, you might have peninsulas. It's where it's a little bit subjective where to draw the lines. And then, as I was mentioning, as for other examples, hills, peaks, passes, and mountains are all in this category. So there are other special cases for geographic features only. Some of them have obvious spatial extents, some of them don't. And it depends a lot on where the information is coming from. So a perfect example of that is a street address. A lot of times using Google Maps, you can look up a very specific street address and see, with a combination of the street map and with a satellite map, maybe, exactly where the boundaries of that address might be. So that's a specific one with a specific spatial extent. In other cases, all that is showing you is a rough idea of where that address ought to be because it doesn't know exactly. And you might be able to determine where it is within a single city block, but you don't know where in the block. So it's a little bit less obvious, and we have to make our extent bigger to accommodate it. Then there are other kinds of features that are based on combinations of real world things, like a path. This could be a hiking path, or it could be a small road, or it could be a superhighway, could be a river. All those are paths. Basically, they could be drawn with a geometry called a polyline, connecting dots in a single path. Another set of features are the crossings of paths, junctions, intersections, and confluences, where things like rivers cross or join, or where roads cross rivers. These are examples of this category. Another one that's a bit tricky sometimes is a headwater of a waterway. Sometimes headwaters begin at the very place where a river flows out of a lake and not anywhere above that. And other times it's very diffuse in some kind of a watershed where a bunch of little streams come down out of the mountains and eventually form something big enough to see on Google Maps. That's some kind of a stream, and that grows and grows into a river. And all that part up above where the waters begin are the headwaters. Then, sadly, we have situations where somebody didn't use our best practices or locality descriptions, and a place is described as near a feature. It's not the feature itself, but it's somewhere around it. That happens. Another one that's not so bad at all, actually, when we think about it, is between two features. Instead of just saying a town, for example, we're saying it's between two roads, it's between two roads. So we have something to bound us very carefully on each side. Sorry, that's the example of between two paths. Between two features would be you have two cities and it's somewhere between the two cities. Other things that are specialized would be things like caves and dive locations, which we have rules for, and the quick reference guide is very good about describing, but we're not going to go into in any detail here. What we will talk about quickly is one of these examples of a special case, which is a street address. So on the top in the diagram A is an example where we're actually able to discern very specifically on the street where the address lies. And we can make a very specific georeference with a center and a radial about just that place on the city block. And the second case is the one I was talking about, where we don't know where it is on the block, but we know what block it's on. And so we can make a georeference that covers just the block and all the possibilities of where that address might be. The second special case is a property. This isn't where a street address comes into play, but rather where there might be some ranch or a farm or a wild animal park that's basically small in size usually, is mentioned, and we can define it by its spatial extent. Sometimes those are very obvious. An example might be a school. You can see the school grounds on a satellite map, and you can draw the boundary around the school grounds perfectly well. In other cases, it's not so clear. Some part of the feature or the property might be very clear. This part is definitely within the ranch, but we don't know how much of the outlying area is part of that ranch. We have an idea, and we need to take into consideration those less obvious boundaries to make our drawing. Sometimes the techniques mean we have to use a corrected center that changes the position to somewhere on a boundary as opposed to where it would lie normally. I won't go into more detail about how we're going to do georeferencing these things. The point here is that we see the kinds of different considerations and that there are actually recipes to follow to do the georeferencing when we come to that point in our learning. Paths, here are two examples. They can be linear features like roads, highways, and trails and streams. But these are things that are subject to change over time, particularly rivers, but also roads. And we have to, if we can, try to have our corresponding map resources be in the same time frame as the event that we're trying to georeference. Here I need to step back and make a caveat statement that is, in our practice doing the georeferencing for the project that we're talking about, what we'll deal with is a set of distinct locations that don't take into account the time when things occurred. So we won't be able to do this specific interpretation of places based on a particular time when we're doing our project. But in good practice for georeferencing, you would be georeferencing specimens, and the specimens would have dates, and the dates would tell you what map sources might be ideal to use for georeferencing. So that's where the time component comes into play. So, and then the final consideration, and this applies to everything, every kind of georeference, not just those for paths, is that large scale maps, that's those with greater detail, are better for actually following the paths locally. They give us more detail, and they can therefore introduce less uncertainty. I will not go into anything further on this slide, I guess, except to say that what we need to do in order to do georeferencing of paths is to find out where to begin and where to end on that path. Sometimes the description says that it's on a road east of another road, and so we start at some intersection and go some distance. And those boundaries are what help us define the feature itself that we're going to georeference. Again, the rest are details about how to georeference and the recipes for doing so, which we won't go into in this presentation. We'll do it later in the course. Here are another example, junctions, intersections, crossings, and confluences. The intersections themselves can be represented by shapes. So in the A part of the diagram, we're looking at a road crossing a river. And in the right part of the diagram, we're taking a little bit of a zoom into there to look at exactly the part of the intersection where the road is on top of the river. So that's the real and detailed intersection of those two places. And it can be drawn as basically a rectangle and georeferenced as that rectangle. That's the junction. Sometimes things are more complicated, like when two rivers meet, because there's no simple crossing. There are actually three segments of river that come together in this place. And the rules tell us how to do this. Basically, we take a line of elevation and we draw a triangle across all three segments of the river at that elevation. And that gives us the thing to georeference. Headwaters of waterways. The first example that I gave when I discussed earlier was a simple one where the river begins where the lake that it starts in ends. And that's this first diagram on the left. So it's just the spot where the river begins. And then other cases where a bunch of tributaries contribute to a larger water body, we have to go through all of the parts of that contributing tributary system to define the headwaters and draw a polygon around all of those things that contribute to the river. And that's that diagram on the right. Then we get into the situation where somebody didn't know any better and described a place as near a feature. You'll find these. Other ways that you might see it are the proximity of, or adjacent to, or any other kinds of qualifiers about the place. The only way we can really deal with that is to make some assumptions and define some distance around the feature itself that means near. And when we do that, like I say, it's not great practice to have written it this way, but we have to try to interpret it. And since it is a subjective interpretation, what we have to do is state the assumptions we made when we interpreted. And that then means it ends up being a rationale that's described in georeference remarks, one of the important fields when we're doing georeferencing, to tell us whenever we had to make a decision that isn't documented in a protocol. That'll come up more than once. Between two features, this is the case where, for example, we have two towns and the area is described as being between them. So in this case, there's a recipe that tells us about how to take the centers of the two features in question and draw what could be interpreted as everything that is meant by between those two things. Between two paths is similar, but in this case, we don't have just two little shapes that are features such as towns. Instead, we have two paths to use as our delimiters. So in the A diagram at the top, one delimiter is a road going east-west, and the other one is a stream or some other small water body also going east-west, and the description says it's between those two things. In B, it's the same kind of description, but it's interesting because the road and river cross in a couple of places, and so between switches sides depending on where we are on that intersection. And so that makes for an interesting special case for georeferencing. So we talked about all of these various special cases to some extent, and cave and dive locations we're going to leave out of the descriptions now. So that was just about geographic features. And you can see that there's quite a diversity. Next, we need to go into the second section with offsets. So offset means distance. And sometimes a description has only a distance. It doesn't say how far. So if you think about this, it's actually a corollary to the near a feature description, except that in this case, somebody's actually telling us what near means. They're giving us the distance. So the example you can see at the bottom of this slide is Bow, 20 kilometers. So somewhere within 20 kilometers of a place called Bow, which means we can draw a buffer around the feature called Bow of 20 kilometers and let that be our feature, our new feature that we need to use as a boundary and to georeference. So again, distance only means no direction was given. It's just how far from a place. Heading only is somewhat similar. We're not given a very full description. It's just that we're told that it's some direction from a place without a distance. So again, down to the examples is the easiest thing to do. And I'll use the last of these examples. West of Devo. So here we're in a situation, we don't know how far west, we don't know where to stop, or at least we're not told where to stop, but we have some sense of direction. In these cases, when you begin to think about it, you quickly run into the question of what does it mean to be west? And so the georeferencing best practices and the georeferencing quick reference guide give recipes about how to interpret directions, both for this situation and for the situation where the heading and offset are both given. So basically, we'll get into how that's done in more detail when we start to talk about interpretations of locations. But basically what we're doing is we're creating a triangle out in the direction that's named from the feature itself, and we're using that as the basis for our georeference. So it's another one of those fuzzy descriptions that we'd rather not encounter. We'd much rather encounter a description like this one. So this is a situation where there is a distance given, and it's specifically given as a distance along some path. So let's go straight to the example again. In this case, the path that they're talking about is route N1. And then the description of the offset is that it's 3 kilometers to the south of some place called Gle. So that's great. We have a starting place, which is the place called Gle. We have a distance to go, and we have a path to follow. So our recipes tell us how to decide where exactly to begin in the intersection between the place Gle and the route N1, and then how to figure out how far to go. It's along that path, so we need to do some measurements. Sometimes it's a straight line. That's easy. Sometimes it's not a straight line, and we have to start measuring along the route as it changes, with many considerations about doing that with precision. Again, details that we'll get into later. This is another locality description type that we would really like to encounter when we georeference, because it's very specific. It's a distance along orthogonal directions. So it's got 2 directions in it. Let's look at the example. 6 kilometers east and 6.5 kilometers north of some place called Juba. Why do we like to see these? Because there is a convention in these kinds of descriptions that when there are 2 directions and they're orthogonal to each other, there's no uncertainty about those directions. In other words, we interpret that description at the bottom, that example, to say, go 6 kilometers due east. Do not waver from east. and then go 6.5 kilometers due north from there without wavering from north to get to our endpoint. The great thing is it takes out all the uncertainties due to direction, which we love. So basically, we're left with the extent of the starting place, in this case, Juba, and some other uncertainties that come into play, like the uncertainty in the distances that we're given in order to determine our final georeference. This tends to be a very a description type with minimal uncertainties. So we like these. Distance at a heading is reasonable as well, and it's very common to find these. In our practices, we found that 45% of locality descriptions are like this. So the example, I'll use the one at the very bottom, 10 kilometers north of Mount Kilimanjaro. So that's an example of an offset, 10 kilometers, at a heading, north, from a named place, Mount Kilimanjaro. Now, if you look at that example by itself, you can see, well, many things come into play here. We've got north, and we just discussed how north can be problematic. We don't know exactly what is meant by north. So it's a triangle northward. We've got Mount Kilimanjaro. It's a big thing. Where do we draw the lines of what is Mount Kilimanjaro, what is not? So these kinds of interesting aspects come into the determination of georeferences. But the type, the locality type distance at a heading, is at least simple to understand and describe and to have a recipe for. Now, distances from two paths. This one gets a little trickier because we've got lots more pieces to play with. The example is 1 kilometer east of MR9, which is a road, and then also at the same time 0.6 kilometers south of this river. So in these cases, what we have to do is we have to get on the map. We need to find the MR9. We have to find the Great Usutu River, get an idea of what those mean, and then start measuring what means a kilometer east of MR9, drawing a line or a polyline, and the same thing with the river, drawing another line or a polyline, in order to get the polygon within which those things seem to be true at the same time. So it'll end up being an intersection, and the uncertainties associated with the kilometers and the directions will end up defining a polygon that allow us to make a georeference for these things. So a little more complicated than the things we've seen before. Those are all the types, locality types, that include offsets. Now we get into ones that are slightly more simple, the coordinates. Paula talked a lot about coordinate systems. We've got the geographic coordinates, of which you've seen all three of the different formats: the degrees, minutes, seconds, the degrees, decimal minutes, and the decimal degrees. Sometimes, as Paula noted, the decimal degrees will come with hemisphere indicators that are letters, but more normally, and the standard way to do it, is by using positive and negative numbers, putting negative signs on when in the southern hemisphere or in the western hemisphere, and then leave that you don't put a plus sign when they're in the north or in the east. You leave them without a sign. But there are other types of coordinates, lots of other types of coordinates. And the most common of the other types of coordinates is a universal transverse Mercator system. So these are systems of northings and eastings, in other words, measurements north or east of some meridian. And those measurements generally are in meters, and they end up being very long numbers. So northings tend to be 7 numbers long, and eastings tend to be 6 numbers long, as they are in meters. But there are tricks. Sometimes when the precision is less, numbers are truncated. So if you look at the second example, the N4291, and the E456. This is a universal transverse Mercator number where they're only giving you the nearest kilometer. Note, universal transverse Mercator systems are not complete just with the numbers in the first two examples. To be complete, they actually require a zone. And the zone tells you where that easting is measured from. It's a meridian and where that easting is measured from. UTM coordinates basically provide strips of longitude that the area of interest can fall within. We don't need to say more about those right now. Another thing that happens, and is actually quite common in South Africa, and I'm not sure how far beyond South Africa in Africa this system is used, but it's a 1/4 degree square system. And I won't go into how that is encoded, but basically what it's doing is telling you a grid square on a map within which the location occurs. So this is all to show you that there are lots and lots of different kinds of coordinate systems. We'll end up doing our georeferences by converting the end products into geographic coordinates, that is, latitudes and longitudes in decimal degrees. Okay, now into the tricky bits, the difficult localities. And there we categorize these. Two of them are interesting in that our recommendation is to not georeference them. The first of these categories is a dubious location. That's where the location description, the actual textual location, tells us that they weren't sure. So examples are possibly Tabatseka. They don't know if it was there or not. The same thing with Wis with a question mark, and the same with Central Democratic Republic of Congo with a question mark. They didn't know, so we don't know, and we decide that those things, those examples, should not be georeferenced. Makes it simple, simple rule. Similarly, we run into situations, and sometimes it depends on how much effort we apply, where the place just cannot be located. Sometimes it's explicit, where the location description says no locality information. It's just completely unknown. In such cases, we have to not georeference it. We've got nothing to go on. Sometimes we have a locality field, but it's filled with a date. The wrong information is there, and so it's the basic similar situation. We have no location information to go on. We can't georeference it. Then there's the other situation where effort probably matters. So here we have a location description, and it looks fine. It's not a date. It looks just like a locality description, but there's some feature in it, a named feature, and we do everything we can to find it, and we just can't. We do a Google Maps search, we do a Google Earth search, we use GeoPic, we use OpenStreetMap, we use Wikipedia, we use a Google search, and the place just doesn't come up. In that kind of a situation, it's perfectly fine to not georeference it. However, in the case where effort had to be made, it's a good thing to describe what you tried to do in order for other people to assess whether or not you did a complete job of looking. So, for example, you would fill georeference sources. This is a field where we capture the maps or gazetteers or resources that were used to do the georeference. We could use the georeference sources to say all the things we tried in order to find the place. And in georeference remarks, say, hey, we tried to georeference this using all those resources in georeference sources, and we couldn't find it. That's why there's no georeference here. So that third case is very different from the other two. And it depends on how much effort you are able to spend to try to find it. Then we get into other tricky bits. The first of them is we do our searches and all is great, except that we find more than one place that it could be. So here there are two possibilities. When two features are related and nearby to each other, so we're not talking about two cities called San Leandro, which are on opposite sides of a country. We're talking about San Leandro, which could be a town, or it could be a river. And the two are right next to each other. In that case, what we have is this first situation, multiple related nearby features. These can be georeferenced, but in order to do it, what we need to do is say it could be one or the other. So our georeference is going to include everything that could be interpreted as one or the other. In other words, we're expanding our georeference to include both possibilities. And that's perfectly fine. But this is a case where we also want to make our georeference remarks declare what it is that we were doing, because it won't be clear otherwise. And part of the process of georeferencing is to try to make it reproducible. And without those remarks, we wouldn't be able to reproduce the georeference. The second case is where the features are named the same thing, but there's more than one of them and they're far apart from each other and so on. So, there are two examples below. One is Independence Avenue in Namibia. There are many of them. The same with a place called Berea, without reference to which higher geographic administrative division it's in. It could be one of many, and it could be across the entire distance of a country or even in multiple countries. And this is another case where we don't want to georeference it, but we want to say why in georeference remarks. Then we have a third situation, which is we have a description, but the information in it is inconsistent. It can't be all of those things at the same time. So the first example is Fomena in Adensi South. Well, in this case, Adensi South, Fomena is not in Adensi South. It's in Adensi North. Here we could make a judgment call and georeference it, but we would have to note our assumption and say, listen, we determined there's no other Fomena than the one in Adensi South. It must be in Adensi North. We're making that assumption. Then we could georeference it, but we have to say all of that. Otherwise, our only option is to say Fomena and Adensi South are not consistent with each other. We can't georeference that. Again, we'd have to say so. We'd have to justify why we didn't georeference it in georeference remarks. In the second case, I'll go through the second example as well. The situation is as follows. We have a description that says 30 kilometers north of Sokode. Sokode is a named place, it's a town. And that is in Chaojo. Well, if you start looking on the map and researching this, and you go 30 kilometers north of Sokode, it turns out that the locality is no longer in Chaojo, it's in Asoli. And so here's an inconsistency where an interpretation with assumptions might be a bad thing, because the Chaojo could be correct and the 30 kilometers is wrong, or the 30 kilometers could be correct and the Chaojo is wrong. And we don't really have a good means to decide which is wrong. In that case, we say, listen, here's the problem in georeference remarks, and that's why we don't georeference it. So I'll leave that one. It should be clear what kinds of inconsistencies can come up, and go to the final example, which is if something is cultivated or captive. So a lot of people, when they approach georeferencing from the beginning, they make an assumption that anything that's captive or cultivated shouldn't be georeferenced. Why have that perspective? Because they're thinking of the perspective of these animals or plants being in the wild, and that their use of that information would be, for example, to create a species distribution model. Well, it's true that these cases of captive and cultivated organisms would not be useful in that case, but that's not the only case for biodiversity data. And we don't want to limit the use of the data by not georeferencing something that can be, when that georeference can be used in a different context from the one we're thinking about. Therefore, the rule is cultivated or captive, yes, georeference it. There's a different way to say that something is cultivated or captive that will allow people to filter out those locations that are georeferenced for those situations and not use them in niche models, for example. And that's the field in Darwin Core called establishment needs. And there it can say that something is native or cultivated. Okay, so that covers the situation or all the examples of difficult localities. And now we basically come to the conclusion about all of those. That is, for any of those situations that we are unable to georeference, basically what we have to do is describe why that is so. And here at the bottom, we have a couple of examples. So for the case where there was an inconsistency, we would write, the locality is demonstrably inconsistent. We can show what things are wrong. And in the case of a location not found, we would say locality not found. And as I described earlier, if we can, fill in the georeference sources with the things we use to look for it. That way, people won't necessarily have to use those same resources to try again if they try to do it in the future. So that's how we deal with the difficult localities. The bibliography for these locality types, their descriptions in detail, and the recipes for how to georeference them are first and foremost captured in the Georeferencing Quick Reference Guide. That's the go-to document to how to georeference. And then the theory behind it and the reasons why the decisions are made for how to do things in the Georeferencing Quick Reference Guide can be found in the much longer and more detailed Georeferencing Best Practices. Those two documents go hand in hand, one for practice and one for understanding in the detail why things are that way. So thank you. That covers our second topic for Module 1 and completes the barrage of information that we have given for you today to try to understand. And I'll pass it over to Paula for some comments on top of that.
Thank you, John. I'm going now to stop the live recording, and I would like to make after some comments